Good afternoon. I'll do wrap up. We're gonna go way too far. Okay, there we go. We've spent a lot of the day talking about FGD water. I'm gonna take a little different approach for the next 20 minutes or so and talk about all the other wastewaters on site and their applicability to these new rules. As we've talked about during numerous presentations, the two newest rules and the two new puzzle pieces in the regulatory outlook are the ELGs and the CCRs. I won't take a deep look into them because we've done that throughout the day. I'll just kind of touch on some highlights and some compliance schedules. As we've mentioned, the CCR rule was published in April of last year, and the ELGs were published in November of last year. Both rules have drivers that are going to require utilities to develop compliance plans. The CCR closure plans by October of this year, and then ELGs requiring compliance as soon as November of 2018. And given those compliance timeframes, project definition studies and preliminary design should be happening now, if not already started. Just a quick couple slides on the rules. Effective January of last year, it applies to, and this is a quote from the rule, facilities where the generation of electricity is the predominant source of revenue or its reason for operation. And the two biggest issues, as we've touched on today, FGD wastewater discharge has very stringent limits, and ash transport water can no longer be discharged. Compliance schedule as soon as possible, starting November 1st of 2018. And then they did put a backstop in. They did put a backstop in of December 31st of 2023. It'll be implemented through facilities NPDES permits, and your permit must justify your compliance schedule. And it's important to note that legacy wastewater is not included. So any wastewater you generate before your compliance date is subject to your old discharge limits. CCR's rule was effective in October of 2015. It's a federal minimum standard. The states can be more restrictive, and CCRs are defined as fly ash and bottom ash, boiler slag, or FGD materials. Each facility has to publish documents on a CCR website, and it allows for citizen suit authority for monitoring. So times are changing when it comes to water flow management at power plants. And with those changes, it's never been more important to know, for utilities to understand what their water balance actually looks like. Present day status quo, most sites have a ash pond or impoundment that all these drains are directed to. So if we take a look into the future, and those ponds are forced to close, what does that new treatment system look like? Well, first of all, you're going to lose your ash streams through ELGs, as well as your FGD waste treatments. Waste streams will need to be segregated and treated separately. So you're left with just plant drains. Easy, right? Single line in, single line out. Question is, what makes up those plant drains? Short answer is a lot. This is a list from a site of everything that was directed to their pond. The two in red are the ones that go away with the ELG. Those in bold are streams that exist at most sites. Upon ash pond closure, these are going to need to be handled and treated in order to meet both existing and future permit limits. And the new treatment options, which we'll talk about in a few minutes, will be much smaller than the ash pond, and with a shrinking process comes less operational flexibility. For this reason, it's becoming very important to accurately characterize these flows and water qualities from these process streams. So how do you do that? Well, a water balance may be a living document. Most are out of date. In fact, it could probably be said that most water balances are out of date as soon as they're printed on paper. So I'd like to take a few minutes and kind of walk you through our methodology and process of helping clients update their water balance. we'll start with a plant survey. We take their existing water balance. We sit down with operations and engineering and try to capture changes, modifications, changes made for operational ease, any equipment that's now being bypassed. We follow this up with a field survey. We go out to the plant, we take P&IDs, we take the water balance, and we walk everything down. Are the as-built correct? Are all of the sources identified? Are all of the users identified? Are all of the discharges identified? And then we do a look and see what kind of online flow measurement is in place that we can grab from the plant historian. Next step would be to try and measure those lines that do not have any flow measurement or intermittent flows. And we do that with temporary flow meters and data loggers. Here's a list of the types of flow meters that we've been using and have available. The picture here is a clamp-on Doppler type. It's an easy installation, quick install, and provides a reliable measurement. We also have insertable magnetic flow meters. You need a 2-inch port, and we can slide this right in. We have Doppler flow meters for ditches and culverts. We'll also, and the previous picture was one on a culvert. This is one installed over a ditch. We'll install rain gauges with data loggers to try and capture precipitation. And then the last thing that we'll do is pump run meters. There's many different styles, but this is a simple meter that basically mounts to the outside of the pump and logs hours when it detects a magnetic field indicating that the pump is running. And so then we use this in conjunction with pumps curves to approximate flows. So with temporary instruments come site-specific challenges. Some of the flows that you're measuring are out in remote locations and they don't have anywhere to plug an instrument in, and your instruments don't necessarily have a long battery life to last 2 or 3 days or longer while you're trying to get a good representative sample. So this is an example where we have hooked up a meter to a solar panel to keep it charged. And then another example is this is a Doppler meter installed over a ditch, and obviously it needs to be over the level of the water, so you can sometimes do very creative things to try and set up an apparatus to allow for that measurement. So in addition to knowing the flows, it's also important to know what the water quality is. And so as part of this process, we'll develop a sampling plan. We'll identify key sample locations as well as what constituents we need to be analyzing. And then frequency is also important. Is it something that we need to monitor once or twice a shift? Is it seasonal? Is it something that, hey, if it rains for an hour or you get an inch of rain or more in a certain duration of time, do you need to go out and grab us a sample? And then we try to capture all the operational variations to the extent possible. And so we take all this and we produce an updated water balance, and then we do some analysis. We try and identify if there are any areas where we can optimize the existing process. Is there any opportunities for water reuse that aren't being exercised? Are there any areas where you could be using a different makeup water source? Obviously, that you'll have to factor in existing materials of construction and compatibility, and then try and identify any operating inefficiencies. So then you end up with a better idea of what your flow rates are. And so here's an example of several flows that go to an ash pond. And after the ELGs, your ash sluice flow will no longer go there. So you've reduced your average flow by 40% or so. And your maximum peak is 55,000 or better. But you'll notice that the majority of that is peak flows related to miscellaneous plant drains, air heater wash, and stormwater runoff. So what do you do? First option is you do nothing. You continue sending it to your impoundment under the premise that your pond isn't going to trigger any of the closure criteria within the CCR, which are dictated by structural integrity, safety factors, groundwater monitoring exceedances, or location restrictions. Now, if you do trigger a pond closure, then you suddenly cut your timeline, and you have a very short window to try and add a new treatment system. So your second option would be, let's install a new process wastewater pond. So here's a picture of a new pond. You can see we've got an inlet mixing chamber. These are your primary settling compartments, access ramps, back unloading pads, and then into a secondary settling area and your outfall. So I've got a new pond. Where am I going to put it? Look at all this real estate. Well, let's start looking at the site. So I've got my existing CCR area, my landfills, my ponds. I don't want to put it there. But I've still got plenty of room. So let's throw in overhead lines, because we'd really like to avoid those, if at all possible. Yeah, it gets a little more crowded, but I've got some areas still out to the far left and far right. Well, except for, let's throw in wetlands, threatened species habitats, dedicated borrow pits, and the community use area like the ballpark we have out on the edge of the site. And suddenly, I'm down to like one optimum spot for my new pond. So I don't have the real estate for a new pond. What's my next option? The next option is to convert to a tank-based treatment instead of a pond. So we'll take the example of, let's say, a 60-acre contributing area for stormwater runoff. We don't have to worry about our FGD flows. They've already been segregated. And we'll put this plant in the upper Midwest. So in a 25-year storm, we can expect 2 inches of rain in about half an hour. So that means my peak stormwater runoff is about 70,000 gallons per minute. So I'm going to design my system for an average flow rate of 6,900 GPM with a hydraulic max of just over 16,000, which means the storage I'm going to need is about 1.2 million gallons to cover that storm surge. So here's a layout of a tank-based treatment system. Maybe. So I've got equalization tanks, and I've got 1 million gallons worth of storage. Oh, but wait, I just told you I needed 1.2. So your other 200,000, we're going to assume can be covered within existing sumps, existing process tanks. Otherwise, these will have to grow slightly, obviously. We'll do a 3 by 50% clarifier configuration. Those are the 3 large tanks to the left, since I can't get the arrow to show up. There they are. Those are roughly 120 to 125 foot in diameter. You may need, depending on your metals permit limits, you may need some polishing filters, and then you'll have your ancillary equipment, chemical feed. Odds are you're going to have to take your pH up to get rid of your metals, which means you then have to bring it back down in order to discharge it. You'll have some coagulants, some polymers. And then you'll need sludge storage and a method for solids dewatering. So what kind of performance can you get out of one of these tank-based treatments? So here's some example guarantees. You can see that we get really good removal on the majority of the constituents of concern in this particular example, better than 95% for TSS and copper, better than 90% for iron, and better than 85% on mercury. Keep in mind that these are for average flows. If you're running through your hydraulic max, your performance may take a bit of a hit. Relative cost and area, you need 3 acres for this tank-based treatment system, and it'll be a $10 to $12 million capital investment, as compared to 15 acres for a new pond at a 6 to 8 million capital investment. I guess I'll end with kind of where I started, with the compliance timeframes. Utilities really need to be kind of in the process of determining what comes next, with regard to not only FGD and their ash, but also with their remaining plant drains. And I'll take any questions. Or not. Yes, we are working on some tank-based systems. Yeah. That's in terms of the area of where to put the new pond. You could, when we were looking at that, that's worst case example where you're gonna clean clothes or cap in place, and so you need to look outside of that area. It's not necessarily the decision has been made, I guess, that you're not going to excavate and line and reuse. Yeah.